So let's start today's tutorial. I hope I am audible, and this is tutorial 10. Okay, so in this tutorial we will be discussing some problems associated to the Radon-Nykodim derivative. Maybe not, I will not get to the Radon-Nykodim derivative today, but some problem regarding the signed measure, and which may help you to solve the assignment 10 for this course. So 10 measure and integration. This is NPTEL email. I think this is 68 email 68, and today is 27th September. Okay, so let me find some problem, and okay, so just a minute. Okay, so today I'll do some, let me find a problem. So first I'll do okay. So let me write a problem. So problem 1 is going on, recording is going on. So first of all, we need sign measure. So let me recall that. If X is be a measurable space, that means X is a non-empty set and S is a sigma algebra of subsets of X. Okay, space. Then a set function, then a extended real valued set function, extended real valued set function mu on S is said to be signed measure, if it satisfies the following three conditions. What are those three conditions? First condition is that mu of empty set has to be 1. Then this is there for the usual measure situation. Second condition is that mu can take at most one value of mu can take at most one of plus infinity, one of plus infinity and plus infinity or minus infinity, one of the values plus infinity and minus infinity on is. Okay, and third condition is that mu is countable additive. Mu is countable. Mu has to be countable additive or disjoint additive means countable additive. Countable additive. Okay. So these three condition. If a measure, if a the extended real valued function defined on the set S is defined on the set of sets S is satisfying these three condition. So then we say that that is a signed measure. So you can look at the usual measure. There is two condition is already there. One is the additive countable additivity, and one is the empty set. On empty set it is zero. But only this condition is extra. That is, it can take extra addition. I mean plus infinity minus infinity. Recall that whenever you are defining the standard measure, that is always taking as the positive measure. So that means that is positive value. That means extended real value, but extended non-negative real value. That was the initial situation. But here we are taking the value is minus infinity to infinity, but it can take only one of the value. I mean, it can at most one of the value. That means there does not exist two sets A and B for which mu of A is infinite and mu of B is minus infinite. So that can't happen. So this is what it is, signed measure. Okay, so with this definition, we'll write a problem. If anything extra needed to need definition, I'll write that. So problem number 1, what it says, let xs be a measurable, xs be a measurable space equipped with a signed measure equipped with a signed measure. That means there exists a signed measure like with the above definition. Signed measure mu, if mu is finite, so that for every E belongs to S, mu of E is equals to supremum of integration over E mod f d mu, such that f from x to r measurable and mod of f is less than equals to 1. This is what it is, the question. So what is question is that x is x measurable space equal to the signed measure mu if mu is finite, so that for every set E, supremum of mod of mu. What is mod of mu? That I'll also define. Mod of mu is equals to supremum of this. Okay, supremum of integration E f d mu, have f is measurable function and with mod of f is less than 1. So this is what it is, the first question. So let me check how to do it. Okay. So recall that mu is signed measure. The signed measure mu is finite if for every measurable set every measurable set E mod mod, this is a real value, this is finite. This is what it is called, the finite measure. Okay. So now and also it is known that this is also Jordan decomposition. Also, it is known that P is finite, so that for every E belongs to S, mod of mu. So it is known that mu can be written as mu plus and mod mu minus, and mod mu is equals to that. Mod mu is equals to, so here is the question is that um, okay, so what is mod mu here? Basically that I must say. It is known that every measure mu can be written as the known that there is two disjoint measurable sets A and B of X with A union B is equals to X, that means disjoint union, then mu plus defined by S2 R plus by, then this by mu plus of E is equals to mu of A intersection E. Okay. Okay, no, this is not all. Then okay, let me complete this one. Then there exists two subset A and B with the property that to disjoint measurable sets A and B subset of X such that A is positive set and B is negative set. So a measurable set E belongs to S is positive or negative set if measure of E intersection F is greater than or equals to 0, or E intersection F is less than or equals to 0, respectively for all measurable set for all measurable set F, okay, belongs to S. So what it says that S, a measurable set E subset of belongs to S, that means measurable, that is said to be positive set if for every measurable set F mu of E intersection F is greater than or equals to 0, okay, or is said to be negative measurable set if for every epsilon greater than 0, sorry, every measurable set F we should have mu intersection F is less than or equals to 0. This should happen for all measurable set. Then E is said to be for positive or negative accordingly. So that means there with this definition there exists a positive set and a negative set. Measurable set positive or set or negative, negative set. Okay, such that A is positive set and B is negative set, and their union A union B equals to X, then the set function mu plus mu minus on S defined by mu plus on a set E is equals to mu of A intersection E for all measurable set E of X, okay, and the mu minus is defined by this way, mu of B intersection E, okay. Defining this way, one will get, okay, sorry, this is minus, yeah, this is minus E intersection A and B intersection A for all E belongs to S. So this way one will get a plus and one will get a minus. So, and then mu is equals to mu plus minus mu minus, and mod mu is equals to mu plus mu minus, okay. So this is the like decomposition of a function f in its positive part and negative part. We know that mod of f is equals to f plus f minus, and f is equals to f plus minus f minus. So this is the thing. We know this all fact I'll just recall, but there is some, and this decomposition is called Jordan decomposition. This is called Jordan decomposition. Jordan decomposition or hand Jordan decomposition, I think sometimes. Yeah. Jordan Jordan decomposition of a signed measure. Okay. So now, so this is what all. So with this way that mu of E is finite. So with this way the mod of mu is actually given by this way. Okay. So this is what it is. So that means mod of mu at the point E is equals to mu plus at the point E plus mu minus at the set E, which is equals to, okay. Now let me come to the question. Now what is the question says that mod of mu E is equals to supremum of f d mu. F is measurable and mod of f is less than 1. Okay. So this is what is the question. So let me try it once again. Now first of all, and with this measure, note that, okay, this is what it is. Now, so first note that for any set for any shape f in for any measurable function f for any measurable function f for which the mod of f is less than with mod of f less than 1, then mod of mu e, which is equals to mu uh, mu plus e plus mu minus e, which is equals to mu of a intersection e plus mu of b intersection e, which is equals to integration a intersection. Okay, sorry, I want to give it little differently. Integration f d mu e, which is equals to can be written as integration e f d mu plus mu is finite. Okay, that is also there. Okay, give me 1 minute. So okay. Yes. Okay, just a minute. Okay, sorry, we don't need to do all these things. So okay, measure mu is finite, so we will be using that one. So what it says, for any function, if for any measurable function f with mod of f less than equals to 1, integration e f d mu, this one is less than equals to integration e mod of f d mod of mu. Okay, so now this is less than equals to integration e d mod of mu, that is equals to mu that is equals to mod mu e, and that is finite, so this is finite. Okay, as the measure is finite, as the measure is finite. Okay, so this is how why this is happening. That if I need, I'll talk later, because this is nothing special. Because if you, I mean, if you can do, then you'll get this one. This is just decompose f in f plus f minus and decompose mu in mu plus mu minus. You'll get this. Okay, so this way, what we are getting here is that supremum of this way. What we are getting, that mod of this way. What we are getting, supremum of mod of f, supremum of mod of f integration over e f of d mu. Okay, this one is actually, this one is actually, in this way what we are getting, that supremum of integration e f d mu, this one, such that f is measurable and the mod of f less than equals to 1. This is less than equals to, this quantity is less than equals to mu of f. Now to get the other around, consider f is equals to characteristics function e. Okay, then what we'll get, then integration of e f d mu, this will be exactly equals to integration over e characteristics function on e and d mu. So this will be equals to mod of mu e. Okay, so I think this is correct. So let me check last one. Integration f d mu is equals to integration e characteristics function e d mu. Then we have to break it little. Okay, so let me check this last quality. So we can break it like integration over e characteristics function e d mu plus minus integration e characteristics function e d mu minus. So now this can be written as this can be written as mu plus e mu minus c mu plus e mu minus e, that is equals to mu of okay, what do you want to get? No, I think to get other around these dips. Okay, immediately for calculate the function of which is the constant value. Okay, let me check the problem again. Constant value mu of ei by mu of e. Okay, so consider the function. I think we have to consider a little differently. Consider the function consider if is equals to mod of mu e by mu of e into characteristics function only. Okay, then clearly mod of f is less than equals to 1 and integration over e f d mu is equals to mu of e mod mu of e by mu of e dot mu of e, which is equals to mod mu of e. So that gives mu of mod mu of, so that means the supremum above, this supremum above attains that point. Okay, so mu of e is equals to supremum. So this means that supremum is attained. That means that there exists basically point is that whatever function we can consider, the last, this one is giving that, this one is giving that whatever function we may consider with measurable function with mod of f less than equals to 1, what will get supremum over integration e f d mu, that is less than equals to mod mu e. But if we consider but if in addition, if we can uh, if in addition, if we can say that like there exists a point exactly equal, so this is what we are getting here. Okay, so that means supremum has to be exactly equals to mu of e. Supremum is always less than equals to this supremum collection is, this supremum collection is less than equals to mu e, but here we are getting that supremum is exactly equals to, so that gives that mod of mu e is equals to supremum of integration f d mu, so that f is measurable function and mod of a less than equal. So this completes the proof. This completes the proof. Now let's find another problem. What it says, let xx be n, let xs be a measurable space equipped with a signed measure mu. Let mu I equals to 1 and 2 be to measure defined on S such that mu is equals to mu1 minus mu2, so that mu plus, that is less than or equals to mu1, and that mu minus less than is equals to mu2. Okay, so what it says, let xs be a measurable space equipped with the sign measure mu. Let mu I equals to 1 and 2 be two measures defined on S such that mu equals to mu1 minus mu2, so that let xs be a measurable space equipped with a sign measure mu. Let mu1 mu2 be two measure defined on S such that mu equals to mu1 minus mu2, so that mu plus is less than equals to mu1 and mu minus is less than equals to mu2. So this is the problem. So no, sorry, I write it little wrong. Okay, middle position with the Philip. This is the another right. Let me change it so that let E is a measurable set so that mod mu at the point E is equal to 0 if and only if mu of f is equals to 0 for every measurable subset f of e. So what it says, let x as the measurable space equal to the sign measurable, e be a measurable set, so that mod of mu equals to 0 if and only if mu of f equals to 0 for every measurable subset f of e. So let's do the problem. Let mod of mu is equals to 0. So that gives mu plus e plus mu minus e is equals to 0. But these two are both are positive quantity, okay? So that gives mu plus e is equals to 0 is equals to mu minus e. Okay, this is what it is. Okay, so one can write as mu is equals to mu plus mu minus. Okay, now let A and B are Jordan decomposition. Let A B belongs to S, B to measurable set such that B to measurable set such that X is equals to A union B, disjoint measurable set B to disjoint measurable set such that this is the Jordan decomposition is a Jordan decomposition Note that Jordan decomposition need not be unique, but the measure defined using the help of Jordan decomposition that has to be unique, that is fixed. Okay, then mu plus of a set A is equals to mu of A intersection E intersection A, and mu minus E is equals to mu of minus of mu of E intersection B. This is what it is. Okay, so now for any subset f of E, mu of f is equals to mu of A intersection f plus mu of B intersection f. Okay, so now because A and B are disjoint, that's why it is happening. So that means this is equals to mu plus f minus mu minus f. This is what it is. Okay, but as A intersection f is subset of A intersection E, that implies mu plus or mu of f is less than is equals to mu of A intersection f, which is equals to 0. Okay, so okay, there is two disjoint measurable sets such that A is positive, B is negative. Okay, so this is what it is means Jordan decomposition. If you recall the definition which we have given there, that A is positive and B is negative, that we have taken. Okay, so with this definition, mu of f is equals to this. So therefore, as we know, any subset of positive set is again positive, so that means this will be positive. Main point is that this will be positive because this is subset of A. Any subset of, so this will be equals to 0. So now, and similarly, B intersection F is subset of B intersection F, that gives measure of B intersection F less than or equals to measure of B intersection E, which is equals to 0, because that is, this is M plus and this is M minus, sorry, mu minus. So you can write it here. This is equals to mu minus and this is equals to 0. This is what we got. Okay, so this gives mu plus F is equals to 0 is equals to mu minus F is equals to 0. This gives mu of F equals to 0. This is what it is, the first condition, right? And mod of mu is also equals to 0. Mu of F equals to 0. Conversely, if for any submeasurable subset, if for any measurable subset subset F of E, measurable subset F of E, mu of F equals to 0, then mu of A intersection F, that is equals to 0, and that is equals to mu of B intersection 0. Why that is? Okay, I think there is one more point is there, x measurable space equipped. Why that is? Because you can check, there is one thing one can be checked. So here clearly A intersection F is subset of F. Now mu of A intersection F, that will be less than or equals to mu of F, that is equals to 0. Now the condition is that mu of A intersection F is less than or equals to 0. So if mu of A intersection F is not equals to 0, that means that is strictly less than. So that is strictly less than. That means that is strictly less than 0. But why that is not possible? So that is not possible. That is what we have to show. Let me try to. That is not possible. That says that what you can write, this A intersection F is a subset of F, right? So that means 0 is equals to mu of F is equals to mu of A intersection F plus mu of B intersection F, right? One can write this, but so if mu of A intersection F is less strictly 0, greater less than 0, then mu of B intersection will be strictly greater than 0, right? But B intersection F is subset of F, that implies mu of B intersection F is less than or equals to mu of F, that is equals to 0. So that means this contradicts to the fact that this is a contradiction. So this gives, so we must have mu of A intersection F equals to 0. So this particular fact gives that mu of A intersection F equals to 0 and equals to similarly mu of B intersection 0. That gives mu plus of F is equals to 0 and mu minus of F is equals to 0. This is what we are getting here. Okay. Now, now, now again the similar argument we will be using. Now mu plus what we have to prove, to prove mod of mu is equals to 0 enough to show okay, I'll do this in the next page. Mod of mu equals to 0 enough to show that mu plus equals to 0. Similarly, one can show that mu minus equals to 0. Similarly, so that mu minus is equals to 0. So why mu plus equals to 0? Because mu plus e is equals to mu of for all subset. Okay. So this is done. As this is true for every, I think we don't need this. All these things are not needed. As this is true for every subset of F, so in particularly for F equals to, as this is true for every subset F of E. So in particular, consider F is E. That it is true for F equals to E. This gives mu plus E is equals to 0 is equals to mu minus E. This gives mod of mu E is equals to 0. So this is all. Okay. So now let's try to find another problem. So problem number 3. What it says, let xs be a measurable space equal to it assigned measure mu compute d mu plus by d mod mu and d mu minus d mod mu. So what is d mu, that I will first discuss, then after that we'll try to solve this problem. Okay. So before that, so we need to recall some things. Recall that to measure mu and nu on the measure space on the same measure space xs is said to be, okay, let me recall those things. Let mu and nu are two sign measure. This is not R, this is B. Let mu and nu be two signed measure on the measurables on S on the measure space XS. Okay, mu and nu are two signed measure on the measurable space XS. Then mu is said to be absolutely continuous with respect to mu, and if mu of E is equals to 0, mu equals to 0 whenever mod of nu E is equals to 0, where E is coming from the sigma algebra S. Okay, and this is denoted by, this is denoted by mu is absolutely continuous with respect to mu. This is what it is, the notation it is given. Okay. In that case, there exists a Radon-Nykodim derivative, and that is what it is called. And in that case, the Radon-Nykodim derivative says that in this case, the famous Radon-Nykodim derivative, Radon-Nykodim theorem, says that let mu and nu are finite measure, okay, with mu is absolutely continuous with respect to nu, then the Radon-Nykodim theorem says that there exists a non-negative function non-negative function. Note that here we are not taking sign measure, here we are taking to define the Radon-Nykodim derivative, to define the absolutely continuous, we can take sign measure. But when we are mentioning the Radon-Nykodim derivative, Radon-Nykodim theorem, that time it is not considering sign measure. It is instead it is considering the finite measure. That means the previous measure till now whatever we are discussing before today. Okay. Then the Radon-Nykodim theorem says that there exists a non-negative function defined on there's a non-negative integrable function f on x defined on x, f defined on x. So f is integrable function with respect to, so there is a non-negative function defined on x, there exists a non-negative function f defined on x which is integrable with respect to nu and such that mu of e is equals to integration over f d nu. This is what it is. Okay. So note that if you have a measure nu and if you start with defining f mu of e is equals to this, so that this holds for every measurable set e of x. Okay. So I mean their point is that suppose you have a measure nu, finite measure nu, or any measures, and you are taking a measurable function f, and if you define d nu, then by this, then suppose you have a measure nu. Okay, suppose you have a measure nu, and and you are defining and take a function f, and you are defining a measure mu, such that mu dot e is equals to mu at e is equals to f d nu. Then what we'll have? Then we have that mu of e is equals to 0 whenever mu of e is equals to 0. Okay, so that means in this case mu is absolutely continuous with respect to nu. But converse is also true, that if mu is absolutely continuous with respect to the measure mu, then there exists a function measure integrable such that this holds. Okay, so this is what it is called Radon-Nykodim derivative, and this function is denoted by, and note that all this thing has been done for the all this thing has been done for the fact that finite measure. Okay, the function is unique in the sense that the function also, moreover, the function is unique in the sense of almost every convergence. Moreover, the function is unique in almost everywhere. Okay, almost everywhere since this function is unique, and this is denoted by, where is that? Okay, this is denoted by, and this function if is called if is called Radon-Nykodim derivative of mu less than mu with respect to mu, and denoted by where is the Radon-Nykodim derivative of mu with respect to mu and denoted by d mu by d nu, which is actually the function f. Okay, this function f is denoted by d mu by d nu. Okay, this is what it is. So now, so this is the Radon-Nykodim derivative, and this is what it is means by this derivatives. But note that this Radon-Nykodim theorem and everything is there for the positive measure. Okay, so that's why for the positive measure we have. So that's why we are looking like this way. Okay, so now let's get back to the question. Question is that compute d mu plus by these two. Okay, also it is note that, okay, these two facts we must know that. Also it is known that it is known that it is known that for any um, signed measure mu plus is absolutely continuous with respect to mu. Similarly, mu minus, this is also absolutely continuous with respect to mu, and mu is absolutely continuous with respect to mod mu. So, and mod mu is absolutely continuous with respect to mu. Okay, so then mu subset of, okay, so let me say mu is absolutely continuous with respect to mu. That means if a set has measure 0 with respect to mu, then that set will have measure 0 with respect to mu, and in that case mu of this can be written as integration f d mu. Okay, this is correct. So therefore, and so this fact, whenever you have these two facts simultaneously for a measure mu, that means mu and mu are two measures such that mu is absolutely continuous with respect to mu and mu is absolutely continuous with respect to mu. In that case, the situation is called absolutely. In that case, that is called equivalent. Then two measure is called equivalent basically. Okay. So but note that the Radon-Nykodim derivative need not be exist. That means the integrable function need not be exist always, unless the situation is that you have a positive, you have the finite measure basically. Okay, but here is note that this absolutely continuous is actually something like transitive type property. So this will give that mu plus is absolutely continuous with respect to mod mu, and mu minus, this is also absolutely continuous with respect to mod mu. So here note that this mod, this mu plus and mu minus, these are both of them are this mu plus and mu minus, both of them are what is called finite measure. That is what we are taking, and mod mu, and that is also finite measure. Okay, okay. So now one can, if these two, so these two happen. So therefore, if these two happens, so therefore one can say that um, if these two happen, so there one can say that, okay, then the Radon-Nykodim derivative, then the, okay, then the Radon-Nykodim derivative, Radon-Nykodim derivative, then the Radon-Nykodim derivative d mu plus by d mod mu and d mu minus by d mod mu exist. Okay, let me to the sign measure come to the exist. Okay, this exist. Okay, exist by, this exists Okay, so now we have to find the this derivative basically. So note that, recall that for any measurable set E, mu plus E is equals to mu of E intersection F and mu plus, obviously you are considering let X is equals to A union B is Jordan decomposition for mu. Okay, that means A is positive set and B is negative set, and A and B are disjoint, and A and B are measurable. Okay. Now, as A is positive, um, now this can be written as mu plus A intersection A. Why? As E intersection A is subset of is subset of a positive set E, sorry, positive set A. So this will, I mean, other around one can say, I mean, if one defines the measure mu by this way, that for any measurable set this way, then this is positive measure. So there is no negative part. This is what it is mean. So, so I mean, basically mu of E intersection A can be written as mu plus E intersection A minus mu minus E intersection B, but B is negative part, so B is actually negative set. So mu intersection, sorry, mu plus of E intersection. Sorry, yeah. This is the thing. So now, yeah. So now as B is, I mean, either way you can say that B is actually negative set. So therefore E intersection B is subset of B. So this will be zero basically. Okay, and E intersection A will be positive. No, here what just a little bit. Mu of intersection A mu plus A intersection A minus mu of E intersection. So this can be written as mu. Yeah, that is what I mentioned. Mu plus A intersection A. This is mu of A intersection A. This is equals to mu plus mu minus A intersection A. Now, as A intersection is subset of A, and mu is positive measure set and this is negative, so that has to be zero basically. Okay, because because A is positive set, A is positive, so this is what it is, a subset of a positive set A. This is the reason. And mu minus, similarly one can obtain mu minus the set E is equals to mu of E intersection B, which will turns out to be mu minus E intersection B. Okay, similarly, then mu plus E is equals to mu plus E intersection A plus mu plus, sorry, mu plus mu minus, okay, and mu plus E intersection A is equals to 0. Okay, so this will give basically. Then mu minus yes, this is correct. Mu minus A intersection equals to 0, mu plus intersection B equals to 0. Now mu plus E is equals to mu plus E intersection A plus mu plus E intersection mu minus E intersection A, because that is 0. This is 0, so we are adding this. So this can be written as mu of E intersection mod mu, mod mu of E intersection A, which is equals to characteristics function of characteristics function. So basically E intersection A, characteristics function on E intersection A, and D of mod mu. Okay, so that means d mu plus by d mu is equals to the characteristics function Ax E intersection A. Okay, similarly mu minus E is equals to what we get. Mu minus equals to mu minus E intersection B, that can be added with mu plus E intersection B, because mu plus E intersection B is equals to already 0. So this will give that mod of mu E intersection B, and that is equals to integration over B characteristics function of E integration B and D mod mu. Okay, we can write this way. So that means what we are getting, d mu minus d mod mu is equals to characteristics function E intersection B. Okay, so this A and B are the Radon-Nykodim. Sorry, this A and B are coming. I mean, these two are the specific. These two are the okay. Mm, sorry, this is what it is. So therefore, this is true for every measurable set A. Okay, for every measurable set E belongs to the sigma, and this is also every E belongs to A. So therefore one can obtain this one actually. This is nothing special. This is the so this is what it is. Characteristics function on B. So I mean basically this can be written as integration over A the function has to be this is okay. This is characteristics function A and this is characteristics function B. So these are the two answers. So this is and this is. So plus part will give. So basically the thing is that plus part will give the characteristics function A and minus part will give the characteristics function. And this A and B are, so you can relate this here that A and B are the positive set and negative set respectively. Okay. Now let's try to find another problem. So this completes the solution. Let's try to find another problem. Well, it says let xs be a measurable set space equipped with a signed measure defined on x. Okay, sorry, I'm letting let xs be measurable space. Okay, this is let xs be measurable space. This is let new and new be finite measure defined on s. Finite measure defined on x. Let f is equals to d nu by d nu plus nu, so that nu is a finite measure, I think, na? Just let mu and nu both be finite measures. Both of them are finite measures defined on sets. Let f equals to d nu by d nu, so that for so that for every e belongs to s, we have mu is equals to integration over e f by 1 minus f d mu. Okay, this is what it is. Okay, so so let's start this. So first of all, note that nu, I think nu here, nu is absolutely continuous with respect to mu plus nu, because mu and mu are both finite measures, so that means they're positive measures. So therefore, this is very natural. So then there exists and f is equals to d nu by d of mu plus nu be the Radon-Nykodim derivative of the Radon-Nykodim derivative of mu with respect to mu plus mu. Okay, then I have to prove this one. So for any measurable set, for any measurable set e of s, e in s, not e of s, e of s, e in s, integration over d nu, this is equals to mu e, right? Integration over d nu, which is equals to integration over e f d nu plus nu. This is what it is, the definition of the Radon-Nykodim derivative. This gives integration f d nu plus integration e f d nu. Okay, that says 1 minus f whole integration over e d nu is equals to integration over e f d mu. Okay. Now, if E is equals to, I mean, we are taking in particular set x belongs to capital X such that the fx equals to 1, then integration over E f d mu is equals to integration over E d mu, right? That is equals to mu of E. Okay. And mu of E is equals to, I mean, in this particular case, so in this particular case, mu, so if this, then above equality gives this. So here we are replacing f is that function. We are considering the function f such that, and considering e is the set where the function is 1. So but the mu of e is equals to basically integration over e f into d mu. Okay. Sorry. Integration, no. This is what we are, so this will be 1 minus f whole d mu. But on the set e, 1 minus f is 0. Okay, so therefore this is 0. As on e, f is as f restriction on e is equals to 1. Okay, this is what it is. So therefore the set where, as the set, so as the set where as mu of e is equals to 0, this gives that f by 1 minus f is well defined function with respect to measure, with respect to measure mu, because the set of measure 0 of 1 minus f is 0. Okay. So therefore, for any function, I mean for the function f, this f by 1 minus f is well defined function with respect to the measure mu as measure of the set x such that 1 minus f at x equals to 0 is equals to 0. Okay, this is what it is. So that's why. So similarly, and as mu is absolutely continuous with respect to the measure mu is absolutely continuous with respect to the measure mu, what it is says, hmm, here is little, just a minute, 1 minus mu is less than equals to mu plus mu. Main point is that we want the set of measure No. And also it is given that this is given. We need here. If mu is absolutely continuous with respect to mu, so that this is what we need. Okay. So here what you can write here is that also given that where you can write given that mu is absolutely continuous with respect to mu, that implies that mu of e is equals to 0. So that implies that f by 1 by f is well defined function. Okay, well defined function. These two are well defined function. This is what we are getting here almost everywhere with respect to the measure mu. Okay, so these two functions are almost everywhere. Let our target is to show that the Radon-Nykodim, that is Radon-Nykodim derivative of, yeah, this is what we need, that mu is absolutely continuous with respect to mu. Okay, so then we can obviously, I mean, if this is the case, then Radon-Nykodim derivative is this one. So then that is d nu by d mu is equals to the function f minus 1 by f. This is what we have to figure. So let g is equals to the function d nu by d mu. Okay, we have to prove that that is equals to f by 1 minus f. Okay, that implies integration over phi d mu, the set full set x is equals to integration over phi and g and d nu over x for every measurable function x, for every measurable function phi. This is true for every measurable function phi. Okay, then integration 1 minus f d nu is equals to integration over x 1 minus f characteristics function over e into d nu, which is equals to integration 1 minus f into g into characteristics function of e into just a minute. Okay, d nu is equals to g d nu. Okay, yeah, d nu. So this is equals to d nu. Okay, so this is on the set x, so this must be on the e 1 minus f into g d mu. Okay, okay, so this gives, but this is equals to 5 from the there from here, so we can write it here from equation 1 can give, so by star. Okay, one can write this one is equals to integration e f dv. Okay, this is for this. This is for every measurable set this. So this gives that f is equals to 1 minus f g, as the above thing is true, as this is true for every measurable set, every measurable set E of E in S, we have f is equals to this almost everywhere with respect to the measure mu, okay, and with almost everywhere with respect to mu and with respect to mu and mu both, because here we have proved for so one you can take inside any of them, like you can for the mu you can take these two, and for the mu you can convert it to, I think, mu to the mu, okay. This gives g is equals to f by 1 minus f almost everywhere. This gives mu of E is equals to integration f by 1 minus f d mu E. So this gives actually the Radon-Nykodim derivative d mu by d mu is equals to g, is equals to f by 1 minus f. No, Radon-Nykodim d mu by d, I think, yeah. Yeah, d mu by d mu. Just a minute. I think this is not needed. No, this is needed. Yeah, this is needed. This is needed. Where there we are using this fact. Yeah, origin. Okay. So these two fact we are making these two. Okay. So this is actually the d mu by d mu. Okay. That last one is the d mu by d mu. So this completes the proof basically. So this is actually interesting problem. So let me quickly go what we have done to solve this problem. So what is given first? Let X be a measurable space, and mu are two finite measure defined on S, and f is a function which is given by like d mu by d mu plus. This is by default it is exist. What is that? That as mu plus mu is, or as mu is absolutely continuous with respect to mu plus mu, so there must exist a derivative of d mu with respect to d mu, the Radon-Nykodim derivative. Now, if mu is actually absolutely continuous with respect to mu, then we can show that the Radon-Nykodim derivative of mu with respect to mu is actually f by 1 minus f. So how to show this one? So first of all, using this fact that f equals to d mu by d mu plus, that means the Radon-Nykodim derivative of mu with respect to mu plus mu is actually f. So then mu of E will be this one, okay? Because f is the Radon-Nykodim derivative. Okay, so this is f is the Radon, that is standard. Okay, so now so basically here f is the Radon-Nykodim derivative, so I can write this way. Okay, so therefore if f is the Radon-Nykodim derivative of mu with respect to mu plus mu, then we can write that integration d mu over E is equals to integration f d mu plus mu. This is what we can always write. This is what is the definition. By definition one can get. So we are getting this one. So from here we are getting this one. So now next what we consider that the set E where the function becomes 1, that is of measure 0 with respect to both mu and as mu is absolutely continuous with respect to mu, so with respect to mu is also. So that means f by 1 minus f, that is well defined function with respect to both mu and mu. Then we have to show that the function g is actually the absolutely mutual Radon-Nykodim derivative. So for this, what we have done, that for every measurable function phi on s measurable function phi, you can write integration x f d mu. If g is the Radon-Nykodim derivative of mu with respect to mu, one can write this one. Okay. Next, we will just use the previous this one and obtain this fact that 1 minus fg is actually almost everywhere equal to the function f, because this is what it is for every on every setting, because these two functions are equal. I mean, integration of these two functions are equal on every measurable setting. So we will be this way we will be obtaining this particular. So this way will be able to prove that this is um, absolutely Radon-Nykodim derivative is this. Okay. So let me go to the next problem. Let mu be any sigma finite signed measure on the measurable space Pn is a power set, that means collection of all subsets of n. Okay. Let mu be counting measure on this measurable space. Let mu be on this measurable space so that mu is absolutely continuous with respect to mu, and compute the Radon-Nykodim derivative of d nu with respect to the measure mu. So here is two measure is there. One is the one any sigma finite measure. Sigma finite measure means that signed measure, in sigma finite signed measure. That means the set n can be written as countable union of sets whose measure mod of the measure is finite. Okay. So here sigma finite measure means, so this is what it is, means that n can be written as a countable union of un such that mod of mu en is finite for all n. So this is what it is. Okay, this is what it is, sigma finite measure. So that mu, and consider mu is counting measure. So basically here it is saying that any sigma finite measure must be absolutely continuous with respect to the counting measure. Okay, so this is what it is says. So we have to find the Radon-Nykodim derivative. So recall that a signed measure mu is sigma finite if n can be written as countable union of n equals to 1 to infinity, countable union of measurable sets, that is en must be in S, such that with mu mu of En mod is finite for all n belongs to the natural number set. This is, I mean, for all n equals to 1 to infinity basically, for all n. Okay. So here is the mother say, here is the underlying mother set is actually n, so that's why this is n. So now what we have to show is that um, first we have to show that, so to show this, so that any absolutely any sigma finite measure is absolutely continuous with respect to the counting measure mu, enough to show that for any subset E of n, because here the sigma algebra is the power set, that means every subset of n will be the element of the sigma algebra. So that means for any subset E of n itself n, if mu of E is equals to 0, then we should have mod of mu at E is equals to 0. So this is what we have to consider. But as mu is counting measure, on the sigma algebra of all subsets, on the sigma algebra of subsets of the natural number n, so mu of E is 0 implies that E must be empty. That implies mu, whatever mu, it doesn't matter, this has to be empty. So this says that mu is absolutely continuous with respect to the measure mu. Sorry, mu is absolutely continuous. Yeah, mu is absolutely continuous with respect to the measure mu. This completes the first part. Now we have to prove find the Radon-Nykodim derivative. So for this, let for any n belongs to n, an is equals to mu at the point n. This is a measurable set. This singleton set n are measurable set. So an is equals to mu n. So this is what it is. We are considering it is an. So and consider the function f from natural number. This is the mother set. These two real number, it will be positive real number. Sorry, this to be the complex number basically. Positive real number, not because this is sign measure, so this can take plus and minus infinity, but with infinity also can take b value. So such that f of n is equals to a. Okay, this is a sequence basically. Clearly new measure of the set n is equals to integration over the set n f of f, basically f d mu. Why this is okay? You can look at, I mean, why it is, because as integration f d mu, the singleton set n is equals to integration an, because on that set particularly this is a fixed value an, and the d mu singleton set, as mu is counting measure and the counting of this singleton set n is 1, so this is actually an. So this is what it is. So that means this is true for n. So then for every subset E of n, mu of E is equals to integration integration a d mu. Here we are using the fact that sigma finite. Why we are using the sigma finite? Because I mean, how we are using the sigma finite, one can say um, How we are using the sigma finite? Um, okay, let me check how we are using sigma finite. Because every set can be written as countable union of sets, subsets basically, right? Or here one can write, I mean, like suppose you have the set E, you can write it as countable division union of n is equals to 1 to some set up to some point, whatever it is there. Okay, I mean, whatever the point, E of the points of in E all will be the singleton sets, and I mean, considering the points in E as the singleton set, one can write E as the disjoint union of those sets, okay, the singleton sets. Okay, one can write this way. So now the measure of the set is actually the summation measure of the set n, and this will give that integration over singleton set f d mu, which is equals to summation over, so which is equals to can be written as integration over f d mu, because mu is counting measure, so this will hold. Okay, so this is what it is. So this gives the Radon-Nykodim derivative of d nu with respect to d mu is equals to the function f. So what is the function f? If actually the function which is defined on the set n that takes the value whatever the measure mu taking the value. Okay, this is okay. This is what it is. Okay, so this is well. Now let's try to do another problem. Problem number. And this is the last problem is fifth problem. This problem is problem 6. What it says, let X be a measurable space. Measurable space. Let mu and nu be sigma finite measure defined on the sigma algebra S, such that mu is unit. This is called equivalent. What is mean by equivalent? That I will say equivalent, so that the Radon-Nykodim derivative of d mu by d mu is equals to Radon-Nykodim derivative of d mu by d mu its inverse almost everywhere. Okay, so here it says that X is the measurable space, mu and nu are sigma finite measure defined on S such that mu is absolutely continuous with respect to nu and nu is absolutely continuous with respect to nu, so that d mu is equals to this one. Okay, so recall that for 2 sigma finite measure equal that basically this is not depending on sigma finite measure for 2 measure for 2 signed measure. The 2 signed measure equal the 2 signed measure mu and mu are called are said to be equivalent if mu is absolutely continuous with respect to nu and nu is absolutely continuous with respect to mu. Mu is absolutely continuous with respect to mu, and this is denoted by mu. This is denoted by and denoted by this is denoted by mu is equals to 3, that almost equivalent. That is what it is. What is the notation? Okay. So the just a minute. So for this, we will be using only one result. One result. This is the known result. So I will be using this one. I think this is also discussed in class. So what it is says, let X be a measurable space if mu mu sorry mu mu lambda r mu and lambda are signed measure, sorry, sigma finite measure. Sigma finite measure defined on the sigma algebra S. Let mu is absolutely continuous with respect to the measure mu. Let mu be a sigma finite measure, sigma finite signed measure defined on S. Defined on S such that mu is absolutely continuous with respect to mu, then d nu by d lambda is equals to d nu by d mu d mu by d lambda. Okay, almost everywhere. This is, so we'll be using this result with respect to the measure lambda. With respect to lambda. So we'll be using these results. So here both of them are sigma finite, so we don't need to consider them any other way, or we don't need to consider this any other way. So, so clearly, if mu is less than equals to nu, then let then if f is equals to the Radon-Nykodim derivative, Radon-Nykodim derivative, this is what we can say, that is that, and d mu with respect to d nu. Okay, and then if g, and then nu, this is nu is absolutely continuous with respect to nu, then consider g is the Radon-Nykodim derivative, be the Radon-Nykodim derivative. Okay, so now point is that clearly what we have to prove that d nu equals to d nu d inverse. So that means if we write here d nu is to d nu by d nu dot d nu by d nu, clearly f dot g is equals to 1, and which is f dot g is equals to, will get mu by nu. Clearly mu is absolutely continuous with respect to the measure mu, and 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 the Radon-Nykodim derivative, and the Radon-Nykodim derivative is 1. Derivative is 1. So that gives that d mu by d mu is equals to 1 is equals to d mu by d mu, and d mu by d mu. So this gives almost everywhere. This gives that d mu by d mu is equals to d mu by d mu inverse. So how this is here is, well, I mean, one factor is that, note that note that uh, or one can consider, mm, my point is that this g, note that the set of x belongs to capital X such that g of x is equals to 0, sorry, g of x is equals to 0. This has measure with respect to g, has to be, g is the function this, so d mu by d mu, this has to be with respect to mu, so therefore mu is 0, mu of this is equals to 0. Why? Because, so the set of measure 0 has 0, then we can write g inverse. This is what my point. Then we can write g inverse as a function. Otherwise, you know. Otherwise, not. Okay. What we have? Yeah, yeah, right. Otherwise, otherwise, this is the, I mean, mu is absolutely constant with respect to mu itself. That means in that case, Radon-Nykodim derivative is 1. So that means this, that means the set of, I mean, this is the function which is 1 everywhere, or almost everywhere on the set X. Okay. Otherwise, uh, otherwise, the point is that otherwise what will have that d mu if, otherwise if indeed this is the case, so this is what I have to prove only. Indeed, if the set E is equals to the set X belongs to capital X such that G of X equals to 0, this is obviously the measurable set, there is no doubt, because G is actually, here we are considering the inverse image of a singleton set 0. So this is measurable. Now, if measure of E is greater than 0, then uh, then the measure of X belongs to capital X such that 1 of X is equals to 0 is greater than 0. This will hold, which is a contradiction. But this is a contradiction. Yeah? Constant function for which constant function is 1. 1 is a constant function which sends every element x to 0. Note that 1 is the, where 1 is the function from x to real number, 1 maps every element to the constant value 1. So the set of, I mean the measure of the set where the constant function 1 becomes 0, that set has measure positive measure. I mean if mu, if the set measure of E is non-zero, I mean uh, if if the measure of the set E is greater than 0, then we will be obtaining that the points where the constant function is becoming 0, that set as measure 0, which is a contradiction. So that's why the G is the set of measure 0 is set of zeros of G has measure 0. So in that case, the G inverse is, so that then, so this will force that G inverse defined what is called this mu almost everywhere. Okay, so this completes the proof, I think. No. Just a minute. Denu. Okay, so this will be. So what we have to prove? It will be denu equals to denu. Yeah, this is correct. Yeah, yeah, this is correct. Yeah, G is equals to denu. So denu exists. Denu is right now denu type. Okay. Yeah, defined almost everywhere. And almost everywhere. So this completes the solution. So this is all for today. I will stop here. Next tutorial is on the next Saturday. Thank you.